Hey math fans! Welcome to Math Olympiad Academy, your trusted space for advanced problem solving and logical reasoning. We sincerely thank our subscribers and all viewers for your continued support. In Lesson 24, we present a rigorous, step-by-step solution to a problem involving the composite function f, composed with g inverse. We first define this composite function, then find its derivative, and finally evaluate that derivative at x equals 2. In this problem, let R denote the set of all real numbers. Let f from R to R and g from R to the open interval 0 to 4 be two functions defined as follows. F of x equals log base e of the quantity x squared plus 2x plus 4, and the function g of x is equal to 4 divided by 1 plus e to the power minus 2x. We define the composite function f composed with g inverse by f of g inverse of x, which means f evaluated at g inverse of x, where g inverse denotes the inverse function of g. Question: define the composite function f composed with g inverse by expressing f of g inverse of x. Then, determine the value of the derivative of this composite function evaluated at x equals 2. Our objective is to understand the method for working with composite functions, how to prove the existence of an inverse function, how to differentiate a composite function such as f composed with g inverse, and how to apply efficient techniques to evaluate its derivative at x equals 2. Before we begin solving, many students have asked me, where should we start with this problem? In this first step, we are given two functions, f from R to R and g from R to the open interval 0 to 4, defined as follows. F of x equals log base e of the quantity x squared plus 2x plus 4, and g of x equals 4 divided by the quantity 1 plus e to the power minus 2x. We now define the composite function f composed with g inverse as a new function h, where h of x equals f of g inverse of x. Now, let's discuss the existence of the inverse of g, denoted g inverse. The function g is defined from R to the open interval 0 to 4 and is given by g of x equals 4 divided by the quantity 1 plus e to the power minus 2x. Since g is continuous and strictly increasing on R, and its derivative g prime of x is strictly positive for all real x, it is 1 to 1. Moreover, as x approaches negative infinity, g of x approaches 0, and as x approaches positive infinity, g of x approaches 4. Therefore, the range of g is exactly the open interval from 0 to 4. Hence, g is bijective from R onto the interval 0 to 4 and admits a unique inverse function, denoted g inverse, which is defined from the interval 0 to 4 back to R. Now, let's find the expression for g inverse. Start with the definition of g of x. G of x equals 4 divided by the quantity 1 plus e to the power minus 2x. Set y equal to g of x, where y is strictly between 0 and 4. Solving for x. Multiply both sides by the quantity 1 plus e to the minus 2x, giving y times that quantity equals 4. Then, e to the power minus 2x equals 4 over y minus 1, which simplifies to the quantity 4 minus y, all over y. Take log base e of both sides. Minus 2x equals log base e of the quantity 4 minus y over y. Multiply both sides by minus 1/2. X equals 1/2 times log base e of the quantity y over 4 minus y. Finally, interchange x and y to obtain the inverse function. G inverse of x equals 1/2 times log base e of the quantity x over 4 minus x, where x belongs to the open interval from 0 to 4. Now, let's find g inverse of 2. Using the expression we just derived, g inverse of x equals 1/2 times log base e of the quantity x over 4 minus x. Substituting x equals 2 gives g inverse of 2 equals 1/2 times log base e of the quantity 2 over 4 minus 2, which is 1/2 times log base e of 1. Since log base e of 1 equals 0, this becomes 1/2 times 0, which is 0. Therefore, g inverse of 2 equals 0. Now, let us determine the expression of the composite function, denoted h of x, which is defined as f composed with g inverse. That is, h of x equals f of g inverse of x. Substituting g inverse of x into the formula for f, we obtain h of x equals log base e of the quantity, g inverse of x squared, plus 2 times g inverse of x plus 4. Notice that this quadratic can be rewritten by completing the square. It becomes the quantity g inverse of x plus 1, all squared, plus 3. So h of x equals log base e of the quantity, g inverse of x plus 1, squared plus 3. However, our main objective is to find the derivative of h. By the chain rule, the derivative of h of x equals the derivative of f evaluated at g inverse of x multiplied by the derivative of g inverse of x. By differentiating the expression for f of g inverse of x, we obtain the derivative of f at g inverse of x equals the quantity 2 times g inverse of x plus 2 all over the quantity g inverse of x plus 1 squared plus 3. On the other hand, the derivative of g inverse of x equals 2 divided by the quantity x times 4 minus x. Then, the derivative of h of x equals the derivative of f evaluated at g inverse of x multiplied by the derivative of g inverse of x. This yields h prime of x equals the quantity 2 times g inverse of x plus 2, all over the quantity. G inverse of x plus 1 squared plus 3, all multiplied by 2, divided by the quantity x times 4 minus x. Finally, this formula allows us to determine the value of the derivative of the composite function f composed with g inverse at x equals 2. To do this, substitute x equals 2 into the expression for h prime of x. Since g inverse of 2 is 0, the first factor becomes 2 times 0 plus 2, all over 0 plus 1 squared plus 3, that is 2 over 4, which is 1/2. The second factor is 2 divided by the quantity 2 times, 4 minus 2, which is 2 over 4. Or again 1/2. Multiplying these gives 1/2 times 1/2, which equals 1/4. Conclusion: the value of the derivative of the composite function f, composed with g inverse at x equals 2, is 1 over 4. I hope you enjoyed this step-by-step solution. Keep practicing, share this lesson with your friends, and don't forget to subscribe to Math Olympiad Academy for more exciting math challenges. See you in the next lesson!